Hello, hello, hello. Nice and chill today. Welcome back. Today is Thursday, the 9th of April. I'm coming in live with a sort of spontaneous session. Wasn't anticipating to get to go live today. Had some free time in the schedule and went, do you know what? It's Easter. You got to grab it where you can. I can see there's already people in the chat, which I love to see. Good to have you guys back. I can see you guys haven't been in a while. Really need a turning points rundown. So today, yes. Now, I am super okay. So today we're doing turning points in physics, and I'm very, very happy to be as led by you guys as possible. I've got my little like AQA online textbook, so I'm definitely supported, planning on just sort of going through top to bottom on that. But this is very much a topic where people have like questions, like what, why, but like why though? And so I'll definitely be keeping a very close eye on the chat to see if anyone has any of those questions today, and then make sure I hopefully get those answered. Because this kind of reminds me of like, I remember the best teaching I ever did was exam season a couple years ago. There was this one guy who was doing IB, physics higher level. No, it wasn't even that. He was just one of my students from physics higher level. And then he texted me at 11 p.m. the night before an exam and went, don't be mad. And I was like, sir. And he said, I have an exam tomorrow and I haven't started studying yet. I'm like, okay. And it was in chemistry, which I don't really cover as much, in medical chemistry. And I was like, I've literally never studied this. So he sends me an online textbook, and in an hour and a half, from like 11 p.m. until half midnight, I read, digest, synthesize, and teach him the entire syllabus. he got a 7, which is the highest you could get in IB. So it kind of reminds me of that. There's like an online textbook, and the way it works is like you just sort of read it, and you're like, well, that doesn't matter, doesn't matter, doesn't matter, doesn't matter. That's the important part. That's the core examinable part. That's like the chemistry part, or in this case, the physics part. So that's kind of how I view this. I've got my online textbook. I'm going to be going through. If I think something's nonsense, I'm not doing it because it's nonsense. Like, could they in theory ask you something about it? Yeah, but is it the core stuff? No. And that's my approach here. I'm not planning to cover every conceivable possible question they could ask you. My goal here is to make sure you've got the core essentials, to make sure like nothing really slips through the cracks. So there we go. I won't be sharing a visual of the textbook just because I don't know if I'm not a copyright person, so I'm just like taking no risks. But we're going to be going to the whiteboard, and I'm basically just going to be copying out everything I think you need. So we're going to start with the electron stuff. We're going to then do the wave-particle duality stuff, and then we're going to end on the special relativity stuff, which is certainly relevant to the AQA, but I think not to the other boards. So you can kind of dip in and out as required. I am keeping a very close eye on chat. So keep your questions coming in, especially as we get to like specifics with some of the experiments. So first things first, let me make sure you can actually see. Let me make sure this can actually write. What does this look like? Great. Because this is I'm gonna zoom in just about just because I like it to be a bit, the pen to be a bit thicker, because then there's like good contrast. You can see really well. All right, so the first things first, we're talking about electrons. How did we find out that there were electrons? Because, oh, and this is like my favorite story. So everyone's like, okay, but when you're talking about current, we say all the time that current is the rate of flow of positive charge. And then it's like, well, why did they do that when we know it's electrons moving through the circuit? To which I say, now we know. Because they had electricity down. They knew what circuits were well before they knew that it was electrons. And so they were like, okay, some charged particles flow in here. Is it positive or is it negative? Is it positive or is it negative? And they coin flipped and they got it wrong. But by the time they actually discovered the electron, it was far too late to change it. So they were like, God damn it. And that's why everything is just wrong. One of my favorite stories in physics. They did lose they took L, and now we're taking the L ever since. So how did they rectify this mistake? How did they find out that electrons were actually electrons, that were actually a real thing? So going through, being supported here from the textbook, drawing out what you need to know. First thing you need to know is what a cathode ray is. So the idea is that we have, nope, go with super strong. So we have a tube. and we connect it up to a super high voltage supply. So say that's negative, say that's positive. Then we know this would be the anode, which is positive. This would be the cathode, which is negative. And what we find is if this is an evacuated chamber, there's very little pressure. That means there are very few. Oh, already a question in. What makes the electron negative? It's not that it decided. It's you're getting into like the deep. It's the opposite of the positive one. We called one positive. We called one negative. The end. They just have things that make them move in electrostatic fields in opposite ways to the other ones. So we called these ones positive, these ones negative. You're getting into some deep like science history stuff that I'm like, that is well above my pay grade. So back to here, we got our cathode tube. It's evacuated. So we apply a very high voltage here. And what happened was you start to get some glowing gas. And the reason why you get the glowing gas is because, as we saw with electric fields, we have charged parallel plates. These are going to have an electric field in between them. With a very high voltage, we know that E equals V over D. And so that's going to be a very strong electric field between the plates. But remember that that is also the force per unit charge. So it means there's very high forces acting on the charges in the gas between the plates. Now that force can be strong enough to strip gas particles of electrons and ionize them. That will make them be positive ions. Now these positive ions are going to accelerate towards the negative plate. When they hit that negative plate, they have a lot of energy. Why? Because there's a large voltage and work done is equal to voltage times charge. So if the voltage is really high, then the work done, which is the kinetic energy, is really high. So they hit the negative plate with lots of energy. In doing so, that can knock the electrons out of the plate. So this is kind of explaining, this is, if you're looking for the details in the book, this is like the 1895, some French physicists did a thing. No, this is the J.J. Thomson one. Doesn't really matter, but the point is, this is the sort of discharge tube operation. So the field ionizes the gas atoms. So then they hit the cathode metal surface. Yes, the electrons are knocked off. Exactly. Causes large numbers of electrons to be knocked off this metal surface. And then what happens is those electrons are accelerated with a massive amount of energy towards the positive plate. And so what happens is these electrons accelerated towards the positive plate. We can see this exact same thing here. The charge is the same, the voltage is the same, so the kinetic energy they have is the same. But because their mass is so much smaller than the positive ions, their speed is so much bigger by the time they reach the positive plate. So these are like super high-speed electrons we're talking about right now. Now, these high-speed electrons, as you saw in your sort of quantum physics, those high-speed electrons can get in and sort of knock an electron out, or they excite an electron to a higher energy level. Bad way of drawing this. Let me try a different way. So you saw that there are the electrons at different energy levels. And so an electron can be excited to a higher energy level and then de-excited to emit a photon. So the kinetic energy of those high-speed electrons can hit atoms and knock electrons into higher energy levels. causing the release of photons, causing it to glow. And this is what a cathode tube ray is. So making sure I'm with the textbook here. So the electrons rejected, high speeds. On striking the ends of the tube, the electrons excited the atoms in the glass, which then de-excited, emitting photons. So this is more of a fluorescent screen that they kind of do this with. But the point is, in terms of the core fundamentals, strong electric field ionizes gas. Ionized gas hits the metal plate, knocking off electrons, which zip to the other end and cause fluorescence on the screen. So they had this thing. They knew this thing was happening. They determined, well, first of all, let's talk more about this sort of emission, because this one is sort of due to ionizing the gas with high voltage, but there is another way you have to know of, which is thermionic emission, which says instead, and this you can do in sort of a total vacuum, which is if you have a sort of cathode instead here, if you make it really hot, that is another way of, because you saw in photoelectric effect that there's this idea of the work function. And the work function is the amount of energy you have to give an electron to free it from the surface of the metal. Now, we kind of saw that here, where we did that by sort of forcing it off with a very strong electric field. That's one way of stripping an electron off. But another way of stripping it off is to give it enough energy to overcome the work function. When you're talking about the photoelectric effect, as we'll talk about later, that's mostly due to incident high-energy photons. Another way of doing that, though, is to heat them up really hot. So if you give them a high temperature, there is enough energy to overcome the work function. And when you do that, the electrons have enough energy to get released from the surface, and that can create your beam of electrons. And similarly, this can be the beam of electrons that goes to hit a fluorescent plate to cause fluorescence. So for instance, if we accelerate it towards like this sort of curved positive anode with a hole in it, they are then accelerated, they have a lot of energy, a beam of electrons can go through and hit a fluorescent screen. Whoop, can I spell? Yes, I can. So that's two different ways of causing this fluorescence to happen. Where we also saw before, as above, sort of here, the work done given to the electron. Now the charge is the charge of an electron. And this gives you the idea of an electron volt. Charge of an electron times the voltage applied gives you the kinetic energy that those electrons have. So that's all here. Cool. So they discovered that there were these beams. They called them cathode rays. They didn't know what was in them. They wanted to work out what was in them. So they're like, all right, what's up? They established that they did have charge. And then the next part of the story that you guys really have to get involved with is determining the specific charge. So this ties in some of the ideas from other parts of the syllabus, making it a good revision point. But there's two ways of doing this. One way is to have those electrons move in a magnetic field, or rather be deflected. Okay, so let's talk about that. Charge plates. Positive plate, negative plate. If I have a beam of electrons going in, we know what's going to happen. They're going to bend up, and they're going to hit the positive plate. Because there's an electric field in between the parallel plates, which exerts a force on the charged electrons, causing them to deflect in a vertical direction. But, so I will put, that would be the electric force. But we also know from Fleming's left-hand rule, if I were to apply a magnetic field perpendicular to the page, we can work out in which direction we would need to apply that magnetic field to cause a magnetic force downwards to balance it. So in that case, the current, if the electrons are moving to the right, that means current is moving to the left. And if I want my thumb to go downwards, it means my first finger, the magnetic field, is acting into the plane of the paper. So if I apply a magnetic field into the plane of the paper, by Fleming's left-hand rule, the direction of the magnetic force would be downwards, and I could adjust the parameters of the experiment such as to make those two forces equal. The electric force acting on the part of the electrons is the electric field. So remember, electric field is force per unit charge. So the electric field strength times E would be the force on the electrons, and we know E equals V over D. And we know the magnetic force on the electrons is given by F equals BQV. But I'm going to call that BEV because these are electrons. Now, a beam would go through undeflected when those two forces are equal. So in that situation, all right, this is not what I wanted though. Hold on a minute, because we need mass to be involved. Okay, no, this is fine. So it is certainly true it's undeflected when these two forces are equal to each other. The way the derivation goes from here, though, is if we take instead this first one, because it's BEV. This velocity is, we have to know, right? So it's when VED equals BEV, little v. This is big V for voltage. Cancels. We need to know little v. So what speed do they have? Well, the reason why they have speed at all is because they were accelerated through one of those cathodes, right? So I'm going to split this up so as to not confuse my different voltages here. But the reason why they have speed at all is because the kinetic energy, the half mv squared they were given to enter this experiment here on the left, they're moving with speed v. This speed came from being accelerated through an accelerating voltage. I'm not going to write accelerating. I'll call it VA for accelerating voltage. Right? So what we know is that half mv squared equals E times that accelerating voltage. And so, moving it down, we can see that E over m, by dividing both sides by m, equals v squared all over 2 times that accelerating voltage. But here we can see that the speed is equal to in fact, if we just call this E times little e instead of VD, I'll kind of show you kind of where it comes from. So E times little e equals that, equals E over B. That is the speed that the electrons must have in order to be undeflected. And if I plug that in here on the left-hand side, then the specific charge is given by E squared all over 2 times the accelerating voltage times B squared. Now, this is where you could say E is equal to V over D. That should have been over. Apologies for making a slight issue there. But the point is, we control what the electric field strength is by choosing the voltage between the plates and the distance between them. We choose the accelerating voltage that we move the electrons through. And we can control the strength of the magnetic field we need to apply in order to make the beam undeflected. And once we have all those measurements, we plug them in, we work out the specific charge. Yes, thanks for catching that. It is V over D for the electric, the force over here. You could also put that in. So I can put that in and say it's V plates squared all over 2 times the accelerating voltage times B squared times the distance between the plates squared. So that might be better in terms of the quantities you actually control. But the point is, we can theoretically derive this expression for the charge per unit mass of an electron, and thus work out what it is. And what they found was that it was about 1,800 times bigger than an H plus ion. And as we know, an H plus ion is just a proton. So it was either it had a bigger charge or it had a smaller mass. And as we'll see, they can work out the charge on an electron. And so they worked out, therefore, it had a mass that was about 1,800 times smaller than a proton. By the way, this was method 1. Method 2 is to just, instead of balancing the magnetic force with an external electric force, is to have no external electric force at all and just have it acting within a magnetic field. Now, as you've seen, a beam of charged particles in a magnetic field, if the magnetic field is perpendicular to the plane of motion of the ions or electrons, by Fleming's left-hand rule, that force will always be perpendicular to the motion, which means it will always be acting towards the center of a circle. Where mv squared over r is equal to BeV for the electron, cancels, V over RB equals E over M. But again, this V, this speed, hold on a minute, where I'm getting slightly... No, let me do this differently, because I want to make sure I keep it very close to the book and don't go off script too much. So half mv, like mv squared over r equals BeV, where these are the same speed. But we also know, again, the reason why it has speed at all is because half mv squared is equal to E times the accelerating voltage. And so what we can do is to plug this in and say that a half times BE, nope. What do they do here? Yeah, I want to make sure I get this precisely. Okay, I see what they did. Apologies. All right. Because again, I want to make sure you guys have very, very specific proofs as required, because that is something they can very much ask. So I was correct to divide by V. So V is equal to BER over M. And that is the speed you can plug in to a half mv squared equals E times the accelerating voltage. So a half times m times BER over m all squared equals E times the accelerating voltage. Is that right? You see, this is how you can tell I've been teaching nonstop since 9 a.m. My brain is not at 100% right now. Hold on, so divided through by V, squaring both sides of the resulting equation. Oh no, this will be fine. This will be fine. Trust myself. Trust the process. M over 2, B squared, E squared, V squared over M squared. That's not a V, that's an R. equals E times VA, one of these E's is going to cancel. That M is going to cancel. And so you get B squared R squared over 2 lots of E over M equals the accelerating voltage. And you can rearrange that to get that the charge per unit mass is 2 times the accelerating voltage all over B squared R squared, where the accelerating voltage you control, the B, the magnetic field strength, you control, and R is what you measure. You measure the radius of curvature of the circle from this experiment. Someone's asking me to explain the right-hand thumb rule. So the right-hand thumb rule is used to explain the direction of a magnetic field around a current-carrying wire. So if we have a current-carrying wire, which is carrying the current directly upwards, the right-hand thumb rule, so if I put my right hand, my thumb in the direction of the current, in this case upwards, if my fingers are wrapping around, they show the direction of the magnetic field acting around the wire. So in this case, the magnetic field would be going around in this direction. And you can use the right hand grip rule to work out, for instance, what is happening on a solenoid. So let's say we had something very much going like this, where this is sort of like going up away from the page and then it's coming down towards me. So this is towards me, this is away from me. What that means is, like, away from me, I can use the right hand grip rule and see that in the middle of the solenoid, the magnetic field line will be moving to the right. And over here, I can do exactly the same thing. On the side that is close to me, my thumb is pointing down, and so I can wrap my fingers around and say that the bit in the middle will have a magnetic field going to the right. And that's how we know the magnetic field direction going through a solenoid. So the right-hand grip rule can be used to work that out, as well as the idea that if you know the direction of the current as you look at one end of the coil, if the current is going around clockwise, that looks like an S, that's the south pole of the magnet. And if it's going the other way around, that is the north pole of the magnet. So you can do it either by the right-hand thumb rule or by looking at the way that the current is moving when you look at the cross-section of the coil. So hopefully you find that helpful. Right, so back to this. The derivation, you kind of got to know how to do it. It's not necessarily intuitive at face value, as you saw, but there are theoretical things that you can put together to derive E over M two ways, one using balancing electric force and magnetic force, and one just allowing the magnetic force to create circular motion. And then finally in this topic, there's the Millikan's oil drop experiment with two significant parts to it. So for the Millikan's oil drop experiment, the idea was that he had drops of oil existing between charged plates. The act of being sort of sprayed out creates some friction which stripped the oil droplets of some electrons and gave them some charge. Not necessarily all the same charge, by the way. So some of the droplets fell through a small hole up here, which I did not draw, and then ended up in a magnetic field. And so what they could do is they could apply a uniform electric field between the plates to create electric force. And so what they can do is, for instance, if the oil drop was negative, by applying the charge such that that plate up there was positive and that one down there is negative, the negative droplet will experience an electric force upwards. Sorry, let me draw this much bigger, because this is looking small on my screen. Let me do this proper. So if we have an oil drop between parallel plates, We have an electric force acting up if that's a positive plate and that's a negative plate, and this is a negative drop. And this acting down is the weight, mg. And so what he did was and again, the electric force, as we've seen before, is equal to E times big E, which is E times V over D. So by adjusting the potential between these plates, you can control the electric force until it balances the weight and causes it to levitate, be completely still in air. And so what he did was he went, okay, when does that happen? Let's do this for a general charge Q, because this was them trying to derive the charge of the electron. So they were like, all right, what is Q? So they know what D is, they've measured that. They know what V is, they've set that to cause it to levitate. Now they need to know the weight of the drop to balance it. Well, the weight of the drop is mass times G. The mass is density times volume. And assuming a spherical drop, that is 4/3 pi r cubed times rho times G. So what they need now is to work out the radius of the drops. Now, to work out the radius of the drops, what they did was they turned off the electric potential between the plates, turned off the electric field, and allowed the drops to fall. Now, because they are so small, the surface area to volume ratio is kind of off the charts, and so the drag force becomes significant that they float down very slowly at terminal velocity. Kind of like when you blow flour in the air and it kind of just slowly settles. And so by kind of magnifying them and sort of measuring how far they move in a set time, you can measure experimentally what the terminal velocity is, and then use a special equation to relate that to the radius. Because at terminal velocity, what we see is that the weight force acting down is counteracted by a drag force acting up, where the drag force is equal to 6 pi eta, which is the viscosity of the fluid you're moving through, in this case air, times r times the terminal velocity. So with a known viscosity of air, with the measured terminal velocity, you can work out r, right? Because that 4/3 pi rho r cubed g, which is the mass, the weight acting down, equals 6 pi eta r v t. We can rearrange this to find an expression for r. So moving the constants to the other side, this would be 18/4, which is 9/2. Pi's cancel. Eta, r cancels to make that r squared. So r squared equals 9/2 eta terminal velocity all over the density times g. And so if you square root that expression, you can work out the radius. And once you've worked out the radius, that you throw up here to work out the charge. Because when these two forces are equal, that is when you can work out the charge. Where that r is what we worked out below. So that is complicated, but it is technically doable. So it's kind of a two-step process. Step number 1, work out the radius from the terminal velocity. Step number 2, plug that into this equation to work out the charge of an electron. They did that. They worked out, guess what? Everything was a multiple of 1.6 times 10 to the minus 19, which is how they worked out that that is the charge of an electron. Whoa! How you guys feeling? Are we having fun yet? Okay. That is part 1. Electron stuff. So hopefully the next part, wave-particle duality, will not be as bad. So the idea here is they were like, dude, what's light? And it was the whole thing where Huygens was like, it's a wave. Yeah, it's a... Don't worry, the others are not going to be that bad, because I think there's a lot less derivation. Because I am not deriving special relativity for you. So this is much more like, just sort of here's what happened. So Huygens was all like, light's a wave. And then Newton was all like, no, but like light's a particle though. And then they were like, no, you're wrong. But Newton had the reputation. And so they were like, okay, Newton's got to be right, right? They were kind of both right and both wrong. It's a whole situation. So they started off by having this sort of corpuscular idea of theory from Newton. And Huygens was like, but it's a wave though. And so what they did was they used the double slit experiment to prove definitively that light has wave behavior. Double slit experiment, interference. This is sort of from your syllabus. The idea is he shone the light through a single slit to make sure it's coherent. So that the only reason for this is to make it a coherent source of waves, or a source of coherent waves. That light gets shone on double slit. So you have these two slits, which then shine onto a screen. We see in reality that light from the two slits travels a different distance to arrive at the screen. When the two waves arrive at the screen, they interfere. The path difference causes there to be a phase difference between the light. And when that phase difference is a multiple of 2 pi, when the path length is a multiple of the wavelength, they arrive in phase and there's constructive interference and you see a bright fringe. When the path difference is n plus a half lambda, when it's half lambda out, when it's pi out of phase, that's what causes there to be destructive interference, causing a dark fringe. If light was made just of particles, they would just sort of fire through and you would just see two bright things, one in front of each of the slits. In reality, we see this interference pattern, which confirms that light has wave behavior. So step 1, light. I'm not going to go through that in too much detail because that's more something when you're talking about waves. I'll do a deep dive then. But that's the thing to revise for that. The explanation for interference and why you get this double slit diffraction pattern on a screen. So that's evidence that it has wave behavior. Do I want to talk? And what they did as well that really sealed the deal. So I'll make a note so that you get interference pattern, therefore waves. Get interference, therefore waves. Now, the thing that really sealed the deal was apparently measuring the speed of light in air versus water, and they showed that it is different, which again supports wave behavior as opposed to particle behavior. So then there's this cool thing in the textbook about how you determine the speed of light. And so there's this whole thing. Do I want to go into this? Is this major? Is this important? Yeah, go on. Let's have some fun. So the idea here is you have a light source. Ding, ding, ding. Super good at art, guys. We have a partially reflecting mirror. Now, the partially reflecting mirror will reflect some light and transmit some light as well. So some of it gets reflected, some of it gets transmitted. So the light that gets reflected gets bounced down here, where it goes through like a sort of toothed gear. And again, super good at art, guys. Proper Da Vinci right here. And then they bounced it off a mirror on a mountain. So it goes through the teeth of the gear, over here to a mirror, where it bounces back and can transmit through this partially reflecting mirror again, and then hit an eyeball. Boop, 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 boop. That's an eye, because that's what eyes look like. So that's the setup. So light travels through a gear, hits a mirror, comes back. So what would you see? Well, the fact that it can only move, if I kind of zoom in a little bit here, the gear's teeth are kind of doing something like this. God, that was going so well for a second. And so there's these gaps, and then there's a tooth, and then there's a gap, and then there's a tooth. So the light can only get through when it's not hitting a tooth. It can only get through a gap. But equally, light reflecting off the mirror can only get back through when the reflecting light hits a gap and not a tooth. And that idea is the idea they use to work out the speed of light. So let's suppose there are n teeth on the thing. So there are n gaps evenly spaced on the wheel. If the time period of the wheel is big T, then the time period to go from one tooth to the next tooth, that little t, is equal to the big time period all over 2n. And the reason why is because you can imagine in sort of one full cycle going between equivalent points, which is the edge of one tooth to the edge of another, half of that time it is spent in tooth and half of the time is spent in gap. So in other words, this is the time to make it through one tooth, and it is also the time to make it through a gap. It is also the time to make it through the next tooth. It is also the time to make it through the next gap. I hope that makes sense. If that does not make sense, feel free to drop it in the chat and I will explain that better. But the idea is this is the time for the one, if you're sort of looking at it, that's the time for one tooth to pass your vision. That's also the time for one gap to pass your vision. Cool. So we have that time period down. Now, the frequency of rotation of the wheel is given by F equals 1 over T. So we can plug that in here and say that's 1 over 2NF. Now, this distance from the gear to the mirror is given by big D, which is like many kilometers. And so the distance traveled there and back is 2D. Now, in order for you to see it, it needs to get there and back. So the light sort of goes in through the gap, it travels there and back, and you have to be able to make it back through the gap before the next tooth comes and blocks you off. So the idea is it makes it through a distance of twice 2D. So the speed is equal to distance over time. The distance traveled is 2D. The time taken is this time we worked out. So speed equals distance over time. Now 1 over T equals 2NF. So the speed is equal to 4NDF. And that was how they worked it out. So they measured D, the distance between where the experiment was happening and where the mirror was. They knew the frequency that they were turning it through. They knew the number of teeth on the gear, and thus they were able to work out the speed of light. So the idea here is that he increased the frequency. So the light was sort of getting through. He increased the frequency until the light was sort of like that just got through the first gap, made it and came back and got blocked. So let me try that again. So he was slowly increasing the frequency until. So he was like when the gear is sort of still. If you imagine the light's going there and back, you can see it just fine. If I start to increase the frequency just a little bit, there's plenty of time to get there and back and to still see it. But eventually you hit a frequency big enough that the light that makes it through, by the time it makes its way back to you, it's now blocked by a tooth. And so the frequency, the minimum frequency required to block out the light is the frequency that you measure and put into this equation. Okay. Yeah, confused AF. Can you please do Astro at one point? Yes, I can. Never been more confused in my entire life. Cool, I'll explain it better. Quite big to make it accurately. Okay, so you're confused. Let me try this again. Because in fairness, I kind of agree. That wasn't my best explanation. I can do better. So, let's imagine, I'm going to imagine sort of being here at this point, at 3 different points. Okay, I'll explain this better. So let's say we're in kind of this situation where this thing is rotating this way. At this exact moment, the beam of light is able to make it through to the mirror and then make it back. Now, as time progresses, those teeth are going to rotate. And eventually, we will hit a point where it's rotating around, where this dot, which is basically the mirror, gets covered up. So at this point, it's just about made its way through the edge, and I can just about see this mirror again. Then it's continuing to rotate, and at this exact moment, the next tooth has come, the mirror's been blocked off. So you have exactly that length of time to make it to the mirror and back before, like, I can't see you anymore. If the gear is still, you have all the time in the world. The light can go there and come back. You're fine, I can see it. And so what he wanted to do, though, was to work out how fast he had to move it to make it such that this time you had between emerging in the gap and getting blocked off again was not enough time to make it there and back. So how do you know if the light returns through the same gap? Well, you know it's not going to be the next gap. So I think I take your point that, like, if it's going too fast, then it would kind of make it back through the next gap. But that's not what he did. They kind of started from 0 and worked out the very first time it got blocked off. So starting from 0, you can absolutely see everything. He worked out how fast he had to turn it so that you get blocked off for the first time. So when that happens, this time period of 1 over 2 NF, that time taken to go from here to here, that time taken where the gap exists, is now officially, for the very first time, because the frequency is high enough, it's now, so basically as we increase the frequency, we decrease that time window where there's and eventually, if you increase the frequency enough, so as we increase the frequency, we decrease the time period. If you increase the frequency enough, you make that time window small enough that it's now no longer enough time to make it to the mirror and back for you to see it. And so at that point, when that time period becomes too small, when the light can't make it there and back, the light that makes it through the gap at this exact point, the very first instance that light was able to make it through, it does not have enough time. It makes it to the mirror, comes back, and bam, it gets hit by the next tooth. Because it was just not enough time to make it back in time. And once at that exact point, you've measured this time period, and that's the time you put in. So at that exact period, C equals, not 2 pi, 2 DNF. Okay. Cool. So hopefully that makes sense. because these experiments can be a little bit difficult to kind of understand. So we've got this idea now. I'm not going to bother going through radio waves and electromagnetic spectrum. That's fine. But basically, we then skip ahead to... Okay, I'm going to be really honest. Based on time, I'm not going to talk about what happens next in the book, which is the photoelectric effect. Instead, I will briefly cover... Still kind of confusing, but yeah, better. I will take the moment to sort of talk about what happens next, which is the photoelectric effect. So I'll just point out the results of the photoelectric effect you need to know, which is that photoelectrons are emitted only above a threshold frequency, never below, no matter the intensity or however long you leave it. The intensity of light only affects the number of photoelectrons emitted and not their energy. The energy only depends on frequency. And below the threshold frequency, you do not get photoelectrons emitted no matter how long you leave it. And so those three results are very important. I encourage you to go back to the book and revise that. But the photoelectric effect is how they proved definitively that light was also had particle behavior. So we did the double slit experiment that proves wave behavior. There's this weird interlude where they worked out the speed of light and proved that the speed of light was different in water and in air. So that's all proving the wave nature of light. Photoelectric effect comes in. That's in your syllabus. That proves the particle nature of light. And so they were like, okay, we've now got to the point. Actually, I will point out just one thing about the photoelectric effect that I think is very important. So I'm not going to go through the whole experiment, but I will get to the point where the EK max equals HF minus phi. And the question then becomes, okay, but how do you measure EK max? And that's the idea of the stopping potential. So what they do is they have the emitting metal surface. They shine some UV on it. UV, that will cause photoelectrons to be emitted. And then we have like a sort of cathode here, or some sort of charge plate here. What we can do is we can apply a voltage. And if we make that a negative voltage, it will repel the photoelectrons. The ones with low energy, they'll get repelled first. But as we slowly start to increase the potential, more and more electrons get repelled away, and fewer electrons have sufficient kinetic energy to overcome the electric potential energy required to make it to the plate. And so by having a very sensitive ammeter and slowly increasing the voltage, eventually you get to a voltage that is so big that all of the photoelectrons are stopped, and that is called the stopping potential. So EK max is the charge on an electron times that stopping potential, and that is how they measure it. So that is the EK max that goes into the E equals HF minus phi equation. So that's just an important point that I really want to touch on while I'm here. The rest of that is very standard for like how your syllabus went and isn't new to the turning points specific stuff. So then they established, all right, so light sometimes acts as waves, light sometimes acts as particles, and then de Broglie came along and was like, okay, but like what if some particles acted as waves? So he thought about electrons, came up with the idea of electrons acting as waves under certain situations, where lambda equals h over the momentum, which is h over mv. And this gives us the idea that, okay, well, if particles can behave as waves, can we make the electrons behave as waves, for instance, diffracting? And this is the basis of all electron microscopes. Where again, they love this idea. So that's MV. You know what I'm going to say. Why does it have that V? Because it's moved through an accelerating voltage, where once again, the charge of an electron times the accelerating voltage equals the half mv squared. That's how we get the speed. That's what gets plugged into there. And so that can be simplified. I'll go through the steps. Equals mv squared. So I'm going to do this in a clever way. So I'm going to multiply both sides by m. So that's m squared v squared. So if I square root this, then I get mv, and that's what goes on the bottom. Where this is the mass of an electron, charge of an electron, and the accelerating voltage I choose to accelerate it through. So you can see, if I can control the de Broglie wavelength by the accelerating voltage I choose. If I increase the accelerating voltage, I will decrease the wavelength. And this means I can control, as we know from diffraction, you get maximum diffraction effects when the wavelength is similar in size to the gap it's passing through. And so it means I can select my accelerating voltage to give the electrons a wavelength on the order of the radius of an atom and get them to diffract through the space between atoms in order to work out like atomic radius, which is quite cool. Stopping potential, just going back, is the amount of potential, because these electrons are flying off from the photoelectric effect. A stopping potential is applied to sort of like repel them. So you only make it, you only make it to this plate that is repelling you if you have enough kinetic energy to start with that you can pay into the electric potential to still make it to the other side. If you don't have enough, you'll get repelled in earlier. So if you slowly increase the negative charge on this plate, you increase the sort of repelling effect, and eventually you'll get to a point where none of the photoelectrons make it to the plate to be measured by the ammeter, and that's how you know that the electric potential equals the kinetic energy. So the electric potential, E times the stopping voltage, equals the kinetic energy. Woo! No, there should not be a cell in the circuit to control the flow of, because the flow is controlled by the UV light, which is causing the. I mean, there should be something that controls the voltage on this plate. You're quite right about that. But the exact circuit is kind of complicated, so I'd rather do this at a high level. How exactly does this prove the particle nature of light? Excellent question, because the results from the photoelectric effect cannot be predicted by wave behavior. Wave behavior says that energy would build up over successive waves, and eventually when enough waves hit it, it would have enough energy that it would escape. So if you just left it long enough, then it would suddenly fly out. In practice, it happens instantly or not at all. Wave behavior also says that energy would be proportional to the intensity of the light. In practice, the intensity does not affect the energy of the photoelectrons. It only affects the number that get released. And in practice, we see that photoelectrons are only emitted above a certain threshold frequency and never below, which again counteracts wave behavior. So the observations of this experiment support particle behavior of light and not wave behavior, because each photoelectron is only emitted from interaction with a single photon. So it proves that light exists as photons. So coming back here to the wave nature of electrons, this is the basis for all electron microscopes. Where again, we can control this accelerating voltage to determine what sort of gap we want it to diffract through. And so we can use a tunneling microscope to see individual atoms, which is awesome. We can also use a scanning tunneling microscope to get a sense of the topography So we can kind of see the up and down of different atoms. So the tunneling is quite cool. Shall I go into this? Yeah, go on. All right, so I'll talk about these two. So the idea behind transmission electron microscope is that similar to a diffraction grating, so we see on a diffraction grating, if I have a diffraction grating, we'll get these beams that come out from the diffraction grating. Could you explain de Broglie again? Yes, so de Broglie wavelength just comes from the fact that if light, which was thought of as waves, can act as particles, does the same thing work in reverse? Can things that act as particles also behave as waves? And so de Broglie hypothesized what, based on what he'd just seen about light, he hypothesized about what would need to be true for particles as well. You don't need to derive this, I don't think. But the idea was from Einstein's work for like the photoelectric effect, he showed that the energy of a photon equals hc over lambda, E equals hf, which is hc over lambda. And from that, he deduced that the photon momentum was h over lambda. And so, well, it's like, hang on a minute, but how can a photon have momentum if it has no mass? We'll get onto that later. But the idea is, all right, well, if these things that act as waves and particles have like this relationship, so this is the particle nature of light here. If the particle nature of light means that photons have a momentum equal to h over lambda, it stands to reason that lambda equals h over the momentum. And it's like, well, what about other things that have momentum? What about electrons? What about particles? And so de Broglie was like, mine, and went, what if electrons did that too? And the answer is, yes, they do. Because we can make an electron beam arrive at a sample, and it causes this sort of diffraction grating beam pattern. And you can analyze where the beams of electrons hit to work out the gaps that they've diffracted through. And so you get some cool results from that. So that's one experiment. This is sort of transmission electron microscopy. So this is your TEM, where you get the sample acts as a diffraction grating, basically. And so you can use the equation that you know from diffraction gratings, n lambda equals d sine theta, to work out what d is, the space that you are diffracting through. And so that is how they work out the gaps between atoms and get sort of atomic radius from that, which is quite cool. By measuring where the beams land. So you can measure the angle difference. You know this is the de Broglie wavelength that you put in. And you can kind of work out from, so the sort of order of beam you see. So this is sort of tying in the syllabus, right? Diffraction gratings showing up, where instead of light being used, you use electrons, which behave as waves, which is pretty epic. Another way you can use this, by the way, is scanning tunneling microscope. So scanning tunneling, you scan over the surface of a material. And the idea here, which is quite fun, is microphone, not a microphone, microscope. So the idea here is you've got your like tip of a thing, and quantum tunneling can happen between the tip of the probe and the atoms of the surface of the metal. So they have this nice ordered structure. And the idea here is tunneling is extremely sensitive to distance. So the closer the tip is to a surface atom, the more electrons tunnel through. And when it moves across, so I'll kind of, so when it's in this position, for instance, that's quite close. You get lots of tunneling. And when we get to this position, we are much further away from it. We get very little tunneling. And so the tunneling is the tunneling of electrons from the metal probe tip. And so we can measure how much tunneling there is by the current. So we can measure a tunneling current using a very, very sensitive ammeter. We can measure the number of electrons leaving and thus determine exactly how far away the tip is from the surface, and thus get a sense of the rise and fall of a surface literally at an atomistic level. So very Princess and the Pea situation. Like you can track atoms on a surface, which is like really cool. So you get these 3D images showing sort of like metal surfaces. So these are applications. Yes, it's kind of complicated, but if I'm going to summarize here like core ideas behind this, all it is we discovered that waves, light behaved as waves from the double slit experiment and from the speed of light in air versus water. We discovered that light behaves as particles from the photoelectric effect. And then we went, okay, well, if that happens for waves of light, can it also happen for particles like electrons? And reverse engineered what their wave-like behavior would be, and we do see that. So now, final thing we got to talk about is special relativity. Now, the Michelson-Morley experiment. Because with turning points, it's basically the experiments that changed our minds about physics. You can only reuse scanning and tunneling microscopy if you're looking at a sample that can conduct the current, right? Ooh. Interesting. Maybe? Ooh, let me have a think about that. Because the it's more about the electrons tunneling from the tip. I suppose. Oh, good question. I used to be able to answer that in my material science degree. Yeah, it's got to be the surface of a metallic or a semiconducting sample. So yes, the electrons do have to have somewhere to go. Quite right. Good catch. Great question. So someone says, I remember asking my teacher and he wasn't too sure. He said they might have some sort of atom-thick layer that can conduct electricity, but then you would only be tracking the surface of that atom-thick layer. You wouldn't be measuring what was underneath. So it would kind of defeat the point of the whole experiment. So in reality, it would be tracking the surface of like a metal or a semiconductor to look at like individual atom placements. So for instance, you would be able to see like the surface of the atoms. And if there was a hole, like you would just see it, which is quite cool. So you can literally just like see the different atoms as like hills on the surface. So with all of this stuff, it's really about like the before and after. Here's what we used to think. We did an experiment. Here's what we now think. Same thing applies with special relativity. So they used to think we were the Earth, we were moving through space, and by moving through space, we were moving through a thing, and that thing was called the ether. There was some sort of ether that we were moving through, almost like how right now we move through air. We can't see the air, but we move through it, but we can feel the wind on our face as we move through it. So, you know, it's like, even if there's no wind, if you're on a bike and you're cycling through it, you feel an artificial wind on your face, slowing you down a little bit. And they thought the same thing would be true of light, that there was an ether that everything moves through. And if you are sort of, instead of riding a bike, if you are a beam of light riding the Earth as it moves through space, that you would feel a headwind if you're pointed in the direction that Earth is moving, and you would be fine if you were pointed in the perpendicular direction. So they wanted to sort of measure the effect of this headwind on the way that light travels. And the way they were going to do that is by using interference. So basic idea. This actually isn't examinable. This is more for your own benefit now. To explain what they were really testing for, we know, for instance, so let's consider two double slit experiments. So double slit experiment number 1, going to a screen here, and double slit experiment number 2 here. It is kind of crazy. It is kind of crazy that light doesn't need anything. It's self-perpetuating. Yeah. We'll get there. It's like bonkers. So we know here, if all else being equal, right here in the middle, what did we say? The paths of light are different lengths. The light travels different distances to get to the screen. That creates a path difference. That creates a phase difference. That affects the interference, the way they constructively interfere or destructively interfere at that point. Under normal circumstances, if light arrives like this in the middle, there is no path difference. They would arrive in phase, and so you would get bright fringe. But let's say we put some sort of filter, a phase filter. That's probably not what that means. But let's say we put some sort of filter on one of the slits now, which changed the phase of the light by 180 degrees. Now, these two beams of light arriving right in the middle have exactly the same distance traveled to that point. They have no path difference, so they arrive with exactly the same phase they left with, which is 100 degrees out of phase. That is now dark. The same point on the screen that was bright before is now dark because I have changed the phase of light coming from one of the slits. This is what they thought they were going to see in the Michelson-Morley experiment. They thought they were going to see a shift in the interference pattern. So I'll kind of show you the setup now, and I'll come back to this idea. I'll tie it in. But the setup of the Michelson-Morley experiment was there was a source of laser light. Make sure I'm still sharing screen. Yes, I am. So there's a source of laser light. We have our old beam splitter, that sort of reflecting. Hold on, let me move this stuff. Well, okay, I'm just going to redraw it. So we have our laser. We have our semi-reflecting mirror. And I'm going to draw it with some thickness, actually, to demonstrate this next point. So if that far side, the light has to go through to the far side, where then some of it gets reflected up and hits a mirror and comes back down and goes through to an observer. So this is laser source. This is an observing viewing telescope. Yeah, I'll call it observing because that's where you do your observations. So this is your observing telescope. Okay. And then some of it, so this is a mirror. This is a mirror. They wanted some of the light to carry on through and come back and down. And they wanted some of the light to get bent up 90 degrees. So that way, again, some of it would go into the headwind of the Earth's motion, and some of it would be fine. But let's track what's happening to this beam of light. So it's kind of going in. It has to go through glass to the mirror, and then through glass to make it to the telescope. So it's gone through glass 3 times. This other beam has gone through glass and then just bounced off and gone down. So it's only gone through glass once. That is why they had to introduce plain glass so that the beam traveling on this other path would go through glass 1, 2, 3 times as well. just to make it a fair experiment. Someone says, my cat is watching, sitting next to me with a lot of interest. Well, let's go. Of course they are. We're talking about laser light. Cats are famously entertained by laser light. So this is the experimental setup. One beam of light traveling sort of gets reflected up and comes down, traveling through glass 3 times. Another goes straight through and then travels down, traveling through glass 3 times. The only difference here, to make this a fair experiment, is the sort of direction that they're sort of going on. So in one case, it would be expected to be moving with and against the ether, and in the other case, it would be expected to be fine. And what they thought was, if I rotate this experiment by 90 degrees, that will be kind of like this situation. It will cause slight differences in the time taken for the light to sort of make it. And that would cause this phase change, which would cause the interference pattern to shift on the screen. Where once there were bright fringes, they'll sort of move a little bit left or right. And that's what they expected. And then what they found was it was utter nonsense. That no matter what they did, no matter because also, okay, let's talk about what could have happened here, right? So let's say, hello, sun, we are Earth, right? So here we're moving that way, here we're moving that way. If there was some sort of actual wind, the ether wind that we were moving through, right? Sort of like cycling in wind. We would get some tailwind, we would get some headwind. And so sometimes we would expect the ether to be with us. Sometimes the ether would be against us. And so what they did was they waited 6 months and did it when we were on the other side of the sun, traveling in the other direction, and nothing they did worked. Nothing created any effect on the interference pattern. And so they were like, I guess we don't travel through ether then. Cool, that's fun. What's up? And then Einstein came along and just did Einstein things, and now we know better. The end. So, am I going to derive this? I'm not going to derive it, but I am going to explain it. That Einstein did a thought experiment where if you if you imagine a sort of train moving past. Hello, yes, I am a train. Hello, yes, I am a person. Art. Person on train has a clock. Clock ticks when light goes there and then light goes back. So it goes there and then it goes there, and that's your tick. Top comment, me equals MC scared. Top joke there. So the basic idea here is we got these things. The speed of light is the speed of light. The distance here is 2L. So 2L, distance equals speed times time. The time taken would be 2L over C in this case. This is on train. So inside the train, this is what would happen. But if you were looking through the window, then you would be seeing that the mirror would be moving and the light would be going ding, ding. And once it here, that creates a tick. Where this vertical distance is still L. But now the horizontal distance for the time taken to get there and back would be, that to there would be v times the time taken, where v is the speed of the train. And you can do some Pythagoras on it. Shall I? Shall I? No. But basically, by doing some Pythagoras on this, you can work out that this time taken would be the true time times this Lorentz factor. Sorry, that's T naught. That's the true time. I need to be precise about this. But this would take longer time because it is clearly traveled longer distance, but taken the same speed because the speed of light is the universal constant. And so it takes longer time. And so we have this Lorentz factor. You probably can't see this. Let me just check. Oh, no, you can see it. So we have this idea of a Lorentz factor, which is given by, Lorentz, is it TZ or is it just Z? TZ. So this is the Lorentz factor. Factor. So the Lorentz factor is gamma, and it is given by 1 over the square root of 1 minus v squared over c squared. Now, here, okay, let's be real. Okay, this is not too bad if you do it right. Here's how you do it right. You don't think about it. You don't really think about what's happening. You just know v and you know c, obviously. So you plug it in, you work out the Lorentz factor. The Lorentz factor is going to be bigger than 1, right? So now you just got to think about whether you want your time to be getting bigger or smaller. Actually, Lorentz will be less than 1 because v is bigger than 0. So this thing will be less than 1. So you're doing 1 divided by something less than 1. Gamma is always bigger than 1. Bigger than or equal to 1, right? So time dilation, the measured time, it's you measuring, you as a stationary observer measuring a moving thing. You observe the time as taking longer than it really is. And so that time goes up. So that's why you multiply by gamma. We also find the same thing with length, only we find length contraction, where the true length that gets a little complicated to sort of get into that. Let's do, I'll do some examples on this one, actually. This is important enough. So let's say we had an observer A traveling on a train of constant speed. So let's say the speed is 0.8 c. Switches on a torch for exactly 3 seconds as the train passes through a station. Another person standing on the platform records the same event, but for a longer time. What time do they measure it for? So what would happen there is, let's work out what gamma is. Gamma is 1 over root of 1 minus 0.64 c squared all over c squared, cancels. So this would be 1 over root of 0.36, which is 1 over 0.6, which is 5 over 3. So that is your Lorentz factor. And we know that if the sort of true time is 3 seconds, the observer of them moving will see it as a longer time. So the time is it is the Lorentz factor times the true time. So it would be 5/3 times the true time of 3, which would be 5 seconds. And that's how that works. So you just start by working out the Lorentz factor and then apply it to the problem, where t equals lambda gamma t naught. And you similarly have an expression for length contraction, which is the observed length is the true length over gamma. So we get smaller. So for instance, this is kind of special relativity comes into play with like muon decay, where there are muons, and based on we know their half-life, and we know the distance from the upper atmosphere where they're created to the surface. And so we know how many of them should decay. And yet far more of them make it than should make it. And the reason why is because we are the stationary thing. So we measure the true length of the atmosphere. They are the moving thing experiencing it. So they experience the true length of the atmosphere divided by this Lorentz factor. So they experience less distance. So they don't think they've been moving as far as they have. So fewer of them decay than should. They experience less distance traveled because they are moving relative to the true length, which is the one that we measure stationary. And does anything else? So the only other thing you need here is this also applies to mass. So as things move, they get more massive. So relativistic mass, they get heavier. This is the basis of CERN, where they make particles go really, really, really fast, give them loads of energy, increase their mass, and then smash them together for fun, because fun. And this is also where, and I'm not going to get too much into it because this is too complicated, so they may actually make the math quite easy. But you also in relativity get E equals mc squared, where this is this is the relativistic mass. So when things are moving, they get more energy. That kinetic energy can be converted into the mass. And so basically, this is the idea then. If you annihilate something, you can convert all of its mass energy into the energy of photons, that kind of thing. So to show you an example of how this would be used, so let's say we had rest energy of something is 106 mega electron volts. Hold on, let me just check. I haven't checked the chat in a while. Nope, we're all good. So let's say we had that. And let's say it started moving. So that's what its energy would be if it was stationary, but it's moving at, now the example given here in the book is 0.9994 C. I'm going to work out gamma. Gamma is equal to, I always do this before doing anything else, 1 over square root of 1 minus that monstrosity, basically that monstrosity squared. 9994 squared. If I type that into a calculator, I get 1 over root of 1 minus 0.9994 squared, which gave me a math error because I didn't plug in a 1, because I type buttons in real good, guys. Super good at it. So this Lorentz factor is 28.87. So in other words, I do 28.87 times the rest energy, and that's the energy it has. So the energy it has is 28.87 times the 106, which gives me basically 3060 mega electron volts of energy. Now 106 energy is basically from the mass, the rest mass, and the remaining is from the kinetic. So the kinetic energy would be the total MeV total minus the 106 mega electron volts of mass energy, rest mass energy. And that gives us 2954 mega electron volts of kinetic energy. So you can use the Lorentz factor to work out the total energy, subtract the rest mass energy to get the kinetic energy. Someone has read somewhere that the density of all nuclei is the same. How is that? Don't atoms have different number of protons, neutrons, some bigger, some smaller? Yes, but remember that density is mass over volume, and the mass gets bigger as you add more nucleons, but the volume also gets bigger as you add more nucleons, and the net effect of that is to cancel out, and the density is always the same. Given that we're basically at the end of relativity, I will answer that question because I know it's in here. Let me get textbook supported. It's a really interesting one. So I actually, while you're here, definitely want to get into that. Turning points, nuclear radius. So this is a kind of niche part of the syllabus, but it is in there, certainly for AQA. So what we find here, experimentally, mass and volume perfectly increase. Yeah, basically. So what we find experimentally, it can be shown that R depends on mass numbers. So what we find is that the radius of a nucleus is given by R naught A to the third, where A is the mass number. So in other words, the number of protons and neutrons. R naught is a constant, 1.05 femtometers. So what happens is the volume of a nucleus is spherical. It's 4/3 pi r cubed, which is 4/3 pi r naught cubed times A. In other words, the velocity is just, the volume is directly proportional to this mass number. Now, the density is the mass over the volume. The mass is the number of nucleons times the atomic, the nuclear U, the average mass of a nucleon. That's the total mass of all the nucleons. And the 4/3 pi r naught cubed A, then the A's cancel. And so this thing is just a constant density, which does not depend on the mass number of the nucleus. And so that is a constant. When you run the numbers, you get 3.4 times 10 to the 17 kilograms per meter cubed. Hello, Vivan. Yeah, no, it's crazy, but this is why it's so epic, by the way. So if you imagine, let's have this conversation. So we know that's the density of a nucleus. We know that the nucleus is about 10 to the minus 15 meters wide, and we know that an atom is about 10 to the minus 10. So that's 5 orders of magnitude difference in the length, which means 15 orders of magnitude difference in the volume. So that is how much of an atom is empty space. The nucleus only takes up one out of 10 to the 15th of the volume of the space that the atom takes up. Which is why when you get a neutron star, when you get supernova, it collapses, all that empty space goes away. And suddenly everything is just the density of a nucleus. It means you would expect the density of the neutron star to be about 10 to the 15 times denser than anything on Earth, because you've lost all that volume. So it's all the density of a nucleus. And I can't remember the exact statistic. I'm sure I'm going to get this wrong, but it was something like 1 tablespoon of neutron star weighs more than the Earth. Like, it's insane. So any nucleus, from the smallest atoms like hydrogen to something big like uranium, all have the same nuclear density? Yes, that is true. Nuclear density is a constant. Not only that, they have the same density as an entire neutron star. So, like, 1 proton, 1 helium nucleus has the same density as a neutron star. Constant density. And part of that, I think, has to do with the strong nuclear force. In fact, there's only so much you can push protons and neutrons together. Like, they have a sort of equilibrium separation. There's something in there. Gotta appreciate AQA for making paper 3 turning points mostly about being familiar with the common questions asked. Yes. So kind of recapping this then. So we had electrons where it was like, we're accelerating, we're applying a big voltage in a gas and we're getting some light. So there's like a beam of something happening. What's happening with that? And then slowly you work out, okay, this thing's charged. Okay, so it's negatively charged. Okay, so we can work out the charge to mass ratio. And then for Millikan, we can work out the exact charge. And then, okay, we've discovered the electron. We've discovered there's a thing with very small mass and 1.6 times 10 to the minus 19 coulombs of charge. That was how we went through that process. Went through a similar process with light. We thought it was like Newton with corpuscles versus like a Huygens wave model. We did double slit experiment and we were like, cool, it is waves. And then we were like, okay, but photoelectric effect, so it's also particles. And then we went, okay, if that's true for light, can it also be true for electrons? And the answer is yes, it can. And we manipulate that in electron microscopes through diffraction effects of its wave behavior. And then with special relativity, What was the point of relativity again, apart from just being cool? I'm not sure there was a clear... Oh, the before and after. Yes, it was the... Are we moving with like an absolute speed? Are we moving through an ether? No, we're not moving through an ether. Michelson-Morley experiment proved that wrong. And so Einstein came along and was like, okay, here's what's happening instead. Came up with relativity. You can do some basic calculations using the Lorentz factor to work on the time dilation, where time appears to get longer for something that's moving, and length contraction, where length appears to get shorter for the moving thing. So as us observing the moving thing, we think the moving thing, yeah. Oh, it's 1 tablespoon of neutron star weighs more than Mount Everest, as per Google. Thank you very much. I wonder how much of a neutron star weighs more than the Earth, because I swear it was something cool. I'm going to Google that. You've inspired me. What volume of neutron star? What volume of neutron star weighs more than the Earth? A volume of neutron star, oh, roughly equivalent to a small mountain. Would be more than the Earth. That's annoying. Okay, we'll go for tablespoon is more than Mount Everest, because that's more practical. But right, I think that is all of Turning Points. I don't see any more pressing questions. I've taken much longer than I would normally take on this, but I've got the time and I thought, hey, let's just do it. Because also Turning Points is just the one you need to do a bit of a deep dive on. I'm not going to claim that that was 100% comprehensive, but I think that's like certainly enough, and it gives you the core essentials. I think in terms of the calculations, practicing working with the Lorentz factor for any sort of calculations there. Also getting to grips with some of those derivations I did for the electron. I know people really struggled with that experiment for how they worked out the speed of light. But also I don't think that is the most important part of the syllabus, and I would be kind of surprised if that came up as opposed to some more important things within the sort of wave-particle duality chapter. So don't worry about that too much. Now, looking ahead, let me look at my calendar real quick, because I don't think I'll have time this week for a live solve. I got that in early by doing 2 last week. It looks like I'll be doing a live solve on Tuesday of next week, followed by maybe an evening stream on Friday the 17th. So those are at least in my calendar. I don't think they should move, which means I can populate them ahead of time and let people know. There's also, I should let you know, a non-zero chance I might do a few GCSE math papers, maybe like 1 or 2, just to sort of get those out there in case people need them. I know I've got some GCSE kids. Teaching them how to check their work might be a good thing. So I might put out one of those, I think probably on Tuesday, make it a bit shorter. So you might be missing out on the math content, but I've done enough math live solves that I think the checking technique is well and good for you guys. So I'm happy to sort of put one out for them and just sort of see if they like it. Now, you guys go off and have a wonderful evening, and I will go off and do the same. And I will see you guys next week. So with that, take care, and I'll see you then. All right, bye, guys.